All right, so this unit, which is chapter 9, is all about complex numbers, which you probably remember as imaginary numbers. So you're going to see a lot of I's in this that represent imaginary numbers. And just so you have an idea of where we're going, we've looked at our normal rectangular coordinates most of the year, so X's and Y's. We just looked at polar coordinates, so R's and thetas. And now we're going to add complex numbers into this and see how all three of those relate and convert between all three of those forms. So if you look at this right here, those first three sections are really focusing on what complex numbers are and how they behave, and then powers and roots of complex numbers, just like we can find powers and roots of the real numbers we usually work with. We'll do powers and roots of complex numbers. And then these two sections, 9, 5, 9, 6, are all about non-real zeros of functions, which we'll look at next week. So to get started, if you turn the page, and if we just looked at this first question here to solve this equation, x squared plus 2 equals 0. Typically what we would do is isolate x, our variable, which would be done by subtracting 2 from both sides. You're left with the equation x squared equals negative 2. Typically, we would then take the square root of both sides, and you would get that x equals plus or minus the square root of negative 2. But this is where we would say, oh, we can't have the square root of a negative, so there's no solution. And that's correct if I asked for all of the real solutions or to solve this over the real numbers. But because complex numbers are what we're going to be looking at now, we will continue and actually solve these. So what would happen if you typed this into your calculator right now? If you typed in the square root of negative 2, I'd like you to do that. So type into your calculator square root negative 2. And what you should get is an error, and if you read the error, it should say error non-real answers, depending on what type of calculator you have. So it should say error non-real answers. But we're going to be focusing on non-real numbers or complex numbers. So if you go to your mode, hit the mode button, and there's a mode that you probably have never switched to before. But if you hit mode and scroll down to the line where you'll actually see the word real highlighted, arrow over, and you should see the option to highlight A plus BI. So if you select that, that's the general form of a complex number, and hit enter, quit out, and then re-enter the square root of negative 2 and see what you get. And you should just get the answer of the square root of negative 2, or square root of 2 times I. Or if, depending on what mode your calculator is in, you'll just get the decimal, so you might just get 1.4142, and then some other numbers, and then the letter I. So notice that when you do change the mode to that complex mode, you do end up getting answers with I to represent. Hopefully you all remember, I is the square root of negative 1. So when you type in the square root of negative 2 to your calculator, it would read it as the square root of negative 1 times the square root of 2, and which would be I times the square root of 2, or the square root of 2I. So let's go ahead and practice simplifying non-real numbers using the letter I. So the square root of negative 11 is the same as the square root of positive 11 times the square root of negative 1, which is just I. So you can think of it as that negative coming out as the imaginary number, or the complex part of the number. And then we have the square root of negative 4 times the square root of negative 9. And So what we'd do is treat the square root of negative 4. That would be the same as the square root of positive 4 times I times the square root of negative 9, which would be 9, square root of 9 times I. Then you would multiply the real parts together, which would be the square root of, or actually the square root of 4 is 2, so we've got 2I times 3I. And then we multiply 2 and 6 together, or 2 and 3 together to get 6. And we multiply our i's together to get I squared. So if you look back up here, if we know that I equals the square root of negative 1, then I squared, if I just simply square the square root of negative 1, you just end up with negative 1. So I squared equals negative 1, which means 6I squared just equals negative 6. And then example 3 is very similar. We've got the square root of negative 36, which is the square root of 36 times I, times the square root of 5 times I. The square root of 36 is 6I times the square root of 5I. So again, we'll multiply our i's together, and we get 6 root 5 times I squared, but I squared is just negative 1. So we've got negative 6 times the square root of 5. So that's how imaginary numbers, or complex numbers, as I will refer to them, behave in simple examples of simplifying. So the formal definition of a complex number is any number that can be written in the form of a plus bi where a and b are both real numbers. So a and b are real numbers, and I squared equals negative 1, or I equals the square root of negative 1. So the real part, we talk about a plus bi as having a real part, and that's a. A would be considered the real part, and the imaginary part would be considered b, or bi, whatever number is being multiplied by I. So this is how we represent complex numbers, a plus bi. And a very important thing that you guys will need to know is that form of a complex number is called binomial form. So you will hear that, not binomial, binomial form of a number is a complex form. So if you hear binomial, complex, imaginary numbers. So you've got the real part, A, and the imaginary part, B. So why would we even use imaginary numbers to begin with? And even though they're called imaginary, they're not actually imaginary. They do exist, so that's why we call them complex. They're very common in science and engineering, physics, economics, all sorts of different fields. You're just not used to working with them as much, and especially when they are called imaginary numbers, sometimes it's easy to overlook them or forget about them, but they are very much useful in the real world. So we actually can graph complex numbers in the same way that we graph normal x's and y's. The plane, we call it the complex plane, but it behaves and looks similar, just like our rectangular Cartesian plane. So in the complex plane, we've got the real axis, so we're used to this being the x-axis, but now we just graph that as any real numbers of a complex number are graphed along the real axis, and then the imaginary part of any complex number is graphed along the y-axis. So to show you, it's a very quick transition from complex numbers, a complex number, to how to graph that on the complex plane. And right here is where I show you what that is. The rectangular coordinates of a complex number are really easy. It's just the x-coordinate is the a, or the real part, which would be 5, and the y-coordinate is the imaginary part, which would be the coefficient of I, which is negative 3. So any number in complex form, a plus b I, can just be represented using the rectangular coordinates a, comma, b, and then you can graph that in the same way you would graph a rectangular coordinate. So if you look at our plane here, and if we want to graph 5 minus 3i, we would go over 5 and then down 3 on the imaginary axis and plot that point. So this would be our point Z. And that's how you graph. So if I wanted to graph another one, say I wanted to graph the point W, which was the complex number -2 plus 4i. Then on my x-axis, or my real axis, which is the horizontal axis, I would go over -2. And then the imaginary part of that number would be +4. 1, 2, 3, 4. And now plot that point W right there. So that's how you go from binomial to rectangular and back and forth. It's a very easy switch. Alright, so we can represent complex numbers in rectangular, polar, and trigonometric forms. So one of these you're not familiar with, but we just looked at complex numbers in binomial form. A plus bi, and I already showed you how to get that to rectangular, which is very simple, just a, comma, b. So an easy switch there, but now we're going to see how do I get a binomial form or a complex form to polar. And if you can get x's and y's to polar, then you can get a's and b's to polar, because those represent x and y. And then next class we'll talk about the trig form, which will be new. So let's first start by taking this complex number z and converting it to polar form. So these steps 1, 2, 3, 4, these are just breaking down the process. It's not much different than what you already know. So first we're just going to graph z in the complex plane to see what it looks like. So if I wanted to graph it, that would just be, think about it in rectangular coordinates. We would graph -3, -5. So -3, -5 would be right here, and that is labeled z. So number 2 says determine the distance of z from the origin. So that would be this distance right here. To determine that distance, well, think about what we already know. We can make this little triangle here, and we want to know this distance, but if you're thinking already in terms of converting x's and y's to polar, that's really r, radius, distance from the pole. So we already know that that's the square root of x squared plus y squared. So if that's -3 and that's -5, then we can solve for r by taking the square root of x squared plus y squared, which would be the square root of 9 plus 5, which is the square root of 34. So that's the distance from z to the origin, or in other words, r. So this step is here is really just saying find r. Next is determine the angle of z from the real axis, meaning that's just fancy for saying what is theta. So here's the real axis, and this line was rotated around. We want to figure out what that degree measure is, and then we've got theta, and then we've converted to polar form. So if I want to find theta, I'm hoping by now that you all remember that if theta equals the inverse tangent, not negative tangent, inverse tangent of y over x, which would be -5 over -3. And using your calculator, type that in. You should be in degree mode when finding inverse tangent, because we want a value of theta that we can understand, so degrees would be best. And we do inverse tangent -5 divided by -3, and you get 59.03 degrees. However, if you look at our our graph, that can't be right. 59.03 can't be right. Well, this is just a reference angle, and a reference angle just tells you from the nearest axis. So 59.03 is that purple angle right there. So obviously, since we know Z where it is, we know that this angle, 59.03, really what we need to do is add 180 to that to get the exact answer. So plus 180, and we get the degree of theta as 239.03 degrees. So we can just round that to 239. So 239 degrees. So the polar coordinate for our original complex number is the square root of 34 for r, comma, 239 degrees. So converting from a complex number, so something in the form of a plus bi, converting that into r's and thetas, you just have that one little extra step. Turn this into a, comma, b, which are x and y coordinates, and then we already know how to turn those into r's and thetas using the fact that r equals the square root of x squared plus y squared, and theta equals inverse tangent of y over x. So not really anything brand new in terms of converting complex coordinates to rectangular coordinates and then to polar coordinates. So this next example, example 2, is going to take the coordinate, if you look at this coordinate, that's given to us in polar form. So we're looking at the value of r and theta, and then our goal is to convert that to binomial form, which is a plus bi. So to convert to binomial form, again, the in-between step of that is converting to rectangular coordinates, because if I know x and y, I can just rewrite that as a plus bi, x plus y times I. So obviously we should know by now how to take a polar coordinate and convert it into rectangular coordinates. This first one, I don't know why it says number 11, but it does. I should just say number 1. Plot W on the polar grid at the right. So r is -4 and theta is pi. If I go out to pi, and then my r is -4, I'm going to go backwards 4, and my point W ends up right here. So we're going to convert that to binomial form. We hopefully by now know that the x-coordinate of a polar coordinate pair is r cosine theta, which is -4 times the cosine of pi. The cosine of pi is -1, and I multiply that by -4 to get +4. The y-coordinate is r times the sine of theta, which is -4 times the sine of pi. The sine of pi is 0, so -4 times 0 is 0. And that should make sense because that point, that ordered pair 4, 0, is right where W is if you were overlaying this with a coordinate x and y graph. So if I want to convert that to binomial form, all I need to do is plug in my x and y as my a and b. So that would be 4 plus 0 I. So we recognize that to be just the number 4. This complex number has an imaginary part, but it's 0, so technically it's just a real number, 4. Alright, so we'll do one more and just convert one more polar coordinate to binomial form. This one's not as easy. We wouldn't be able to just figure it out from where it is on the polar grid. So if we graph our point Z, 5 pi 6 is our angle of rotation. So to help you know where that is, because our polar grid isn't labeled, but if this is pi right here, then 5 pi over 6, which is just 1 pi over 6 less than 6 pi over 6. This would be 6 pi over 6, because that reduces to pi. Then 5 pi over 6 would just be 1 less than that, which is right there. So I'm going to erase the lines I just made, but just to reason through where that would be we've got 5 pi over 6 right there. I'm just going to erase the mess I made. No, I'm not. It's not working. Okay, well that's where 5 pi over 6 is. And then our point, our r is 4, so we'll go out 4, 1, 2, 3, 4. And there's our point z. And we're going to convert that to binomial form. And again, anytime you see binomial, if you need to write it out, a plus bi. The in-between step from getting from polars to binomials or complex is rectangular coordinates in between. So really, you just have that one extra step at the end to convert to binomial, but what we're really doing is converting to rectangular first. So to convert to rectangular, again, the same relationship that we've been using for a few weeks, x equals r cosine theta, so 4 cosine 5 pi over 6, which is 4 times cosine of 5 pi over 6, which is negative root 3 over 2, which we can reduce to negative 2 root 3. So that's my x-coordinate, negative 2 root 3. And I'd like you to use exact values when you can. We know that 5 pi over 6, we have those exact values for our trig values on our unit circle, so we can do that. Our y-coordinate is 4 times the sine of 5 pi over 6, which is 4 times 1/2, which is 2. So there's the rectangular coordinates. And from there, to convert to binomial, it's the quick step of just taking our x-coordinate, that's our a, that's our b, so it's negative, 2 root 3 plus 2i. So that's binomial form of our polar point z. The real part of that is negative 2 root 3. The imaginary part of that would be 2. So that's all we're going to do for today for these notes. So what I want you guys to be able to do is questions 1 through 4 on the 9.1 worksheet. And all you are asked to do is you're given one form of a number. I might give you something like this and ask you to, first of all, name what that is. So that would be binomial. And then convert that to both rectangular and polar form. So you should be able to go back and forth between all three forms now, starting with rectangular. You should be able to take rectangular and convert to binomial. And polar. So all three of those going between back and forth in either direction. So I want you to try that on questions 1 through 4 on the 9.1 worksheet.